Principal component analysis. So again, principal component analysis is a unsupervised learning algorithm. So that is used for dimensional reduction in the machine learning. Okay, so we have seen a brief introduction about what is dimensional reduction in the previous video. So what exactly is principal component analysis? It is a statistical process that converts the observation of correlation features into a set of linearly uncorrelated features with the help of orthogonal transformation. So this is what is the definition which we came across in the previous video itself. So the new transform features are called as principal components. So these are the new features or the parameters or columns or whatever you want to mention it as. So again, principal component analysis, PCA in short, it is one of the most popular used for explanatory data analysis and predicting models. So it is a technique to draw the pattern. Sorry, it is a technique to draw the pattern, draw a strong pattern from the given data set by reducing the variance. Okay, so PCA generally tries to find the lower dimension surface to project the high dimensional data. Okay, so PCA works by considering the variance of each attribute because the high the high attribute shows the good split between the classes, hence it is dimensional reduction. So basically what it means is it will consider the variance of each attribute. So every attribute over here again means with respect to individual data, because the high attribute shows the good split. Okay, so when you have a high attribute of the data, then it is a very good split with respect to classes, hence the dimension hence it reduces the dimensionality. Okay, so some real world again applications is like as mentioned in the previous video, it is like image processing, movie recommendation, optimizing the power allocation in various communication channels. Okay, so uh, again power plays a huge role if you're familiar with respect to data transmission or communication. It can be wired or wireless also. So you will have multi channels. Definitely if you have optimization, so with respect to the features over here, so all the features from different channels can be reduced into few features and decide ultimately with respect to which channel power should be allocated at the particular instance. Okay, so it is an extraction technique again, feature extraction technique. So it contains the important variables and drops the least important variables. Okay, so that is what is happening over here. And there are PCA algorithm is actually based on a mathematical concept such as like variance and covariance and eigenvalues and eigenvectors. Okay, so just refresh these concepts. So with respect to variance and covariance and eigenvalues and eigenvectors. Okay, so there are a few terms which will be commonly coming across with respect to PCA algorithms. Again, we already know most of them. So first is dimensionality. So it is dimensionality is nothing but the number of features present in a given data set. So all the features, parameters, columns, like I would like to tell columns because usually when you start up with the working of projects, so it is very easy to remember when you're importing a comma separated table or Excel spreadsheet. Okay, so it will have the columns. So all these columns are features. You won't be having features in rows, it will be columns itself, and individual data would be in the rows. Okay, so data points, all the data points will be located on the rows. So dimensionality, so number of features. Okay, so number of two-dimensional, three dimensions. Okay, so even with respect to visualization we can consider that. And next is correlation. So correlation or correlation, so this we have come across in the previous videos also. So basically it signifies us that how strong two variables are related to each other. Okay, such that like if one changes then the other variables will also change. Okay, so you can expect you can evaluate this behavior with respect to the data set itself. So you can consider two features. Again, we were discussing with respect to high correlation, right? With respect to feature select common techniques used in dimensional reduction. So there are high correlations, and I was telling like the relation between like having the decimal in example we had given like 14 and 14.25 in different feature. In one feature it can be 20 and other feature is of 20.21. So it will be like very close by. Okay, so that is what it is. So usually when one is changing like comparing like 14 to 20, so obviously 14.25 to 20.2 or 20.1, so something it is changing, right? So this change is actually very close to each other, and usually the correlation value ranges from plus or minus 1 itself. Okay, so here like minus 1 occurs if the variable is inversely proportional to each other, and positive side means it is directly proportional to each other. Okay, so that is about correlation. So it's all about the relationship between the two data points of or you can consider a data point of two different features, data point with having two different features or many features. We'll be comparing two features. Next is orthogonal. Okay, so even we saw about orthogonal transformation. Again, it defines the variable are not correlated with each other. Okay, so it is the variables that are not correlated with each other, just the opposite. So hence the correlation between these variables will be likely to be almost zero. Okay, so it is actually like zero itself. So hence the correlation between any pairs or variables we consider is zero. Okay, so that is orthogonal. And next we have eigenvectors, eigenvalues, and eigenvectors. So if there is a square of if there is a square matrix M and non-zero vectors is given, then the vectors will be eigenvectors as the multiple or the multiplication of with a constant is a scalar multiple of phi. Okay, so just refresh with respect to what exactly eigen value and eigenvectors are. So that is one, and final one we have already seen. So basically this is used for getting with respect to the accuracy. So like no, not accuracy. So basically this is with respect to the covariance matrix. So here it will tell the uh, variation between variables. Okay, so what is the covariance? Okay, again the mathematical terms we were speaking about variance and covariance, right? So this is here covariance, so we'll represent in terms of matrix. So this matrix will have covariance of each of pairs of variables, so hence it is known as covariance matrix. So few terms which is commonly used in PCA. Again, if you are working on one of the example project, it will be giving more insights and have a better understanding with respect to all these terms. So again, knowing basics is the best. Again, next we'll see the steps involved in PCA. So again, PCA, like as I described earlier, the transforms new features or outputs of PCA are actually principal components. So number of um, are say the number of PCs or principal components should be equal or lesser than the features itself. Okay, so if you have only 2 or 3 features and you are trying to like do again apply principal component, maybe you will end up with equal to or lesser than. Okay, so if you are having equal to, that doesn't make much sense, so you should have lesser than itself. So there are some properties also with respect to principal component. Okay, so they are like the principal component must be linear combination of the original features. Okay, so again the combinations would be linear, and these components are orthogonal, so that is mean the correlation between the pairs is zero, and the important of the each component decreases when we are going with 1 to n, means like one principal component is the most important, and then the next n or the last, like wherever the n principal component will be the least important component. So basically it will have the weightage. So first principal component might give you 70% of accuracy. Second, if you consider the another principal component, will give you somewhere around from 70 to maybe 95. So the first principal component has the most important, so it is giving 70% of your accuracy. Just an example, and the next one is like reduced down by 35. So next one would be probably 1 or 2%. Okay, again speaking that with respect to in terms of final accuracy outcomes with so many principal components. So now let us see steps of principal PCA, principal component analysis algorithm. So getting started with data set. So firstly we'll always import the data set, or we'll have the inputs of the data set and then subdivide it into two things. So one will be the training data set, uh, other would be test data set. So we had already seen like repeatedly we have come across like we'll be splitting the data set into training set and test set. So usually, let me give more insights. So usually the training data set will be given as X and test data set would be given as Y. Okay, so representation of variables. So X will be the training data set and Y will be our test data set, or you can sometimes it is called as validation data set too. So that is the first step of PCA, and next is representing the data into structures. So now we will represent our data set in terms of a structure. Okay. So basically what happens is such as will represent the two-dimensional matrix of an independent variable X. So here each row corresponding to the data items and each column corresponding to the feature. Okay. So the number of columns in the dimensions of the data set. Okay. So represent each data into structures, so individual structures, and then we will standardize the data. So standardizing or normalizing we had already come across, right? So this standardization step, like we had seen an example where the mean would be somewhere lying around 1010 and or 990, if I recall correctly, 1010, and you will have a little standard deviation, right? And you might have like this is for one particular feature. If you are going for another feature, you might end up having the same thing, but there will be measure of spread. Okay, so there will be different spreads, one like spreading over 110 and another might be spreading over on an average of somewhere around 50 or 0 itself. So standardization is required because if you are like considering with respect to numeric values, definitely the value having like spread across 1010 or around 1000 with definitely with respect to number weightage it is more. Okay, so if you are directly applying covariance or like going on with eigenvalues or eigenvectors, so those will have a higher weightage. Okay, so those will be considered those will automatically have higher weightage or more significance, but that won't be the case, right? So each individual feature will have its own significance, so that's why we need to standardize. So in this step we'll be considering particular columns. So the features with high variance are the most important compared to the features with lower variance. So if the important of features is independent of the variance of the feature, the features is independent of the variance, then we will divide each item into the columns with the standard deviation of the columns. Okay. So again, with an example, it would make much sense over here with respect to the standardization. Again, we have a lot of Python libraries which will be doing that. So basically, the steps is important. If you just recall this step, the third step is to do standardization and apply standardization. There you go. You will be getting a better accuracy with respect to your machine learning model. And next step is calculating the covariance of Z. Okay. So to calculate the covariance, so that will be taking a matrix, so matrix Z. So then we'll be making a transpose of it. After transpose, we will just multiply a value of Z. Okay, so that will be the output of the covariance of matrix. Okay, so covariance of matrix multiplied with the value Z. Okay, so we are just getting covariance, and next we will be calculating eigenvalues and eigenvectors. So here like with respect to the resultant covariance matrix, eigenvalues or eigenvectors can be calculated. So eigenvectors or the covariance matrix are in the direction of the axis. Okay, so axis with the high information, and coefficients of these vectors can be defined as eigenvalues also. Okay, so coefficients of individual eigenvectors are defined as eigenvalues. So after getting the eigenvalues, we'll be sorting these eigenvalues. So maybe for eigenvalues you can use NumPy. Okay, so that will directly fetch your eigenvalues. So in this step, we will take for sorting. We will take the eigenvalues and sort them in maybe decreasing order, which means the largest to the smallest, because we need the most significant ones at the beginning, right? So we'll we'll just arrange them in decreasing order and simultaneously sort the eigenvectors according to the matrix of the eigenvalues. Okay, So the resultant can be known as some kind of a matrix. The resultant matrix can be known as a P, okay, just for principle, something like that, or a P star, and then we'll calculate the new features or the principal component. So here we'll calculate the new features. To do this, we'll just multiply P star, okay, the newer P star with respect to the covariance Z. So the resultant would be, again, you can consider as Z star. So each observation is in linear combination of the original feature. So each column of the Z matrix is independent of each other. So it will be again independent of each other, and finally we'll remove the less or unimportant features from the data set. Okay. So all these steps will be taken, like if you are working with an example, it will be like taken care in one single shot. So it is pretty straightforward. Okay. So the main steps, what I would like to tell is getting the data set, then standardizing it, calculating the eigenvalues, and finally removing the unimportant features. Okay. Or with respect to some of the Python libraries, you just need to mention with respect to how many dimensions you are looking for, and it will automatically carries out with respect to eigenvalues, eigenvectors, and directly give us final uh, principal component features. Okay, those data will be given, and again applications, various AI applications also are there, like computer vision and all. So it can be used for finding hidden patterns in high dimensions. So some fields where PC are used are like even finance, data mining, and even psychology, and so on. Okay, so that is about principal component analysis.